So I'll be discussing assignment number 10 in this particular doubt solving session. So the first question said that which of the following is true. So the first, that is compliance and stiffness matrices must be positive definites. So as we already know, these are the equations which um, connect the stress and strain values together. This is the stiffness matrix. If we know the value of stress, we can compare them, we can multiply them with the stiffness matrix to obtain the strain values. And similarly, if we know the strain values, we multiply it by the compliance matrix to get the stress values. So we can see that compliance and stiffness matrix both are material properties, and therefore these would definitely be positive and definite, as material properties are independent of the direction in which the force is applied, and they're also specific to given material, so they would be definite. Then the second said that the number of independent elastic constants for generally orthotropic and specially orthotropic materials are different. So the only difference between generally orthotropic and specially orthotropic material is the orientation of the fibers, and therefore we can like see that the number of elastic constant would be same in both the cases. However, their values will be different. For specially orthotropic, some of the terms would be zero. However, while representing the matrix, you'll have to write all the constants. So therefore, the number of independent constant would be same in both the cases, and B is false. Then she said that for isotropic materials, Young's modulus and shear modulus are always positive. So again, Young's modulus and shear modulus are both material properties. Material properties will always remain positive and definite for a given material, and only the stress and strain values will be positive or negative depending on the kind of force you are applying. If it's tensile, then it would be positive. If it's compressive, then it would be negative. So therefore, Young's modulus and shear modulus being material properties will always be positive. Therefore, A and C are correct for question number 1. Then in second question, it's asked that what would be the strength of this material? That is, what is the maximum stress at which this composite would be breaking? So this is a lamina in which all the fibers are oriented along 45 degrees, and a unidirectional tensile loading is applied along x-axis. That is, sigma L is sigma x is the only stress which is applicable, and this is unidirectional tensile force. So for this, sir derived this formula in his lectures. Just need to substitute all these values into this particular formula. I've substituted it here. The sigma x, that is the maximum stress the composite will bear, depends on the value of theta, which is 45 degree in this case, and sigma x is what we need to find, while these all are the material properties which we know. Now sigma Lu is the ultimate strength of the material, longitudinal strength of the material when tensile load is applied, while sigma dash Lu is when compressive loads are applied. So therefore, sigma Lu will be used because unidirectional tensile loading is applied. So these upper material properties would be used, and this would be the shear strength value. So we substitute all this together, we get this answer, which is same as the solution given. Then we repeat the same thing when the fiber orientation is 60 degree instead of 45 degree. You again substitute all these values in this particular equation and solve, you get the same answer. Now for isotropic material, which of the following statement is related to the stiffness matrix is true? So in his lecture, sir has already derived stiffness matrix a couple of times for three-dimensional composite laminates. So we can see this is the relation between specially orthotropic material. For isotropic, both the directions, that is along 1, 2 and 3, in all three directions, it would all be same. Therefore, most of the constant will be same, and this would be true. Then in fifth question, they have asked that which of the following statement is true. The first one is that difference between generally and specially orthotropic material is function of a reference coordinate system. So in one of his questions, he has taken this as reference. This was a case when pure shear stresses are applied. So this is when fibers are oriented around 45 degrees and shear stress is applied. Now the reference plane is changed from this to this. Now we can see this lamina has transformed from generally orthotropic material to specially orthotropic material, and therefore we can see that the difference only comes between the reference coordinate system. Rest of the properties can here or less be transformed when doing calculations. Then the B option is that the stiffness matrix for a generally orthotropic materials contain 36 non-zero elements, and 36 elements are obtained only from 9 independent elements. So these 9 independent elements are the material properties like the Young's modulus, the moments, the shear modulus along different directions. And these 36 elements, as illustrated in this matrix is for specially orthotropic material. So obviously there would be some zeros here, but for generally orthotropic, most of the elements have definite values and zero is not present in this matrix. Sir has explained in his lectures. So we can say that 36 non-zero elements would definitely be present, and yes, they would all depend on 9 independent elements. Like we have done for 2D matrices, the similar would be done for 3D matrices, and you'll find that they depend only on 9 independent elements. Now the C option was that transversely isotropic material only has 4 independent constants. So we already know that isotropic materials depend only on two independent constant. Transversely isotropic material would also behave similarly, and therefore this C option is incorrect. A and B are the only correct options. Now in sixth question, they've asked that a graphite epoxy lamina shows the following strength properties. Now Sahil theory is to be used to estimate the maximum off-axis shear strength of the laminate for fibers oriented at 30 degrees. So it's also given that we need to consider that only positive shear stress is applicable. So a similar question has been discussed in the lectures too. We take that tau xy is positive, and therefore this equation is used in which the sigma L value is taken to be tau xy cos square theta, while sigma t is taken as minus tau xy sin square theta. You can refer to sir's lecture of week 10. You'll see one of the lectures illustrates this particular problem in detail, while the shear stress value is taken to be 0 in this case. Once you solve this particular equation and substitute all these values here, you'll get to see that the tau xy value is 165.8, which is similar to the answer provided. Then seventh one talks about the stress transformation matrix and the strain transformation matrix. Stress transformation matrix is when we have components of sine theta and cos theta to convert from one reference plane to another. Strain transformation matrix is also something similar. So, sir has already discussed a lot about stress transformation and strain transformation matrices and their interrelative properties. This is also a direct question, so you can just refer to the lectures if you have further doubts on this. Then eighth question is about how many independent elastic constants are there in each of these materials. So monoclinic materials are crystallized structures which have a specific arrangement. We have not talked much about monoclinic materials here. Then orthotropic materials are the one in which one direction is has higher values, while the directions which are perpendicular to that initial material axis have far different properties. While anisotropic are ones in which properties are different in all the directions. In orthotropic, properties are different when you take a perpendicular turn, but in anisotropic, properties are different in all the directions, like individually. Then transversely isotropic materials are where most of the properties are same along all the directions. So from the previous derived cases, we can see that anisotropic material are the one which have most independent elastic constant, and therefore the answer is C. Now in ninth question, they have given a compliance matrix for specially orthotropic composite lamina. That is when fibers are oriented along 90 degrees direction or 0 degree direction. And they have tried to derive the compliance matrix when fibers are oriented at 40 degrees instead of 90 degrees. So this is the generalized matrix and the formulas which are used. Sir has already explained this in class. So you just need to derive this q bar 11 value, like this particular matrix, from the matrix which is given here. This Q11 value would be 30, Q12 would be 1.4, like so on. And once like I've done for the first equation, Q11 bar would be 30 times this Q1 30 times cos to the power 4 of 5. 5 is 40 degree here. Once you substitute everything here, you'll get the answer to be 12.53, which matches here. You do similarly for all these 9 equations, and the matrix exactly matches. The 10th question is the repetition of this one. Only in this particular question, you'll use theta to be 30 degrees instead of 40 degree. The answer matches overall. So yeah, that's it. You just need to put these particular equations using this particular matrix, and you'll get the new reformed compliance matrix. So that's all for assignment number 10. Anyone else has some doubts? Good evening. Yeah, good evening, Krishna. Yeah, that it's a little difficult to remember. Actually, you don't need to remember whenever you apply these things. They are mainly applied when you're dealing with large level structural mechanics. Okay, so you'll have to use ANSYS, MATLAB, COMSOL. You just need to feed it initially, and then it will automatically give the stress values. And this is used for explaining the results which are obtained. Fine. Try to remember it a little, just the basics. As it is, they won't ask. Fine. Okay, then meet you on next Monday. Thank you. Yeah. Okay.